right, so I just want to emphasize. Let's get started, guys. I just want to emphasize that the rules that we talked about yesterday, and that we could still use the graphical stuff that we've talked about, the table stuff that we've talked about for limits at infinity. But the algebraic rules that we talked about yesterday, the rationalizing and the simplifying, those all have to do with x approaching a number. Today we're going to talk about as x approaches positive or negative infinity. So it's important to keep the two rules, the two ideas separate, because we treat the two separately. So I want to start with an example. Let's say we have f of x equals this nice rational function, 2x over x plus 1. And we want the limit as x approaches infinity of f of x. Well, we know a little bit about rational functions and what their graphs look like. So what can we figure out about the graph of this function, of this rational function? So what do we have to be careful of with rational functions? X can't be negative 1. What happens to the graph when x equals negative 1? Is there a hole? Right. There's only a hole when we have a factor, the same factor in the numerator or denominator. So we don't have a factor of x plus 1 in the numerator and denominator. So what happens when we plug in negative 1? We're dividing by 0. So what does that tell us? What happens to our graph? Vertical asymptote. We have a vertical asymptote at x equals negative 1. Not here. And rational functions also have horizontal asymptotes. You remember how we find the horizontal asymptote of this thing? Degree of the numerator and degree of the denominator are the same. So our horizontal asymptote is at the ratio of the leading coefficients. What's the ratio of the leading coefficients? 2 over 1. So we have a horizontal asymptote at y equals 2. And if we plugged in some points to see where our function went with this, between these asymptotes, we'd get it looking like this and looking like this. So as x approaches infinity, way out here, what value is the function getting close to? 2. Limits at infinity have to do with the end behavior. They have to do with the end behavior of our function. So what we're talking about when we're talking about limits at infinity are horizontal asymptotes. And so our rules for finding limits at infinity are exactly the same as our rules for finding horizontal asymptotes. Yes?
But it never actually reaches to
So we said the limit, all we care about for the limit is what it gets close to. We don't care what it equals, we just want to know what it gets close to. So, yeah. So limits, that's what the limit is looking for. What does it get close to? Since it gets close to the asymptote, that's our limit. But you're absolutely right, it never actually equals 2. Gets close to 2, gets as close as we want it to 2, it's never actually equal. So our limits at infinity have to do with the horizontal asymptotes. Our rules are the same. So and when we work with these algebraically, there's only one rule that we need to know that tells us why those rules for horizontal asymptotes work. So our rules for limits at infinity, or our rule, and this is the rule that really tells us why we could do those things before when we found the horizontal asymptotes. The limit as x approaches, and this is plus or minus infinity, of 1 over x to the n power equals, and before we write this down, let's think about this. If I divide 1 by a really, 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 really big number, what happens? It gets really, 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 really small. So this limit is going to be 0. And n is a positive real number. That's the only rule that we need to know that we're going to work with for limits at infinity. 1 over x to the n, limit as x approaches positive or negative infinity, is 0. So what I want to do is go through several examples and relate this idea to our rules for horizontal asymptotes, and then talk about some really nice shortcuts for remembering these rules, remembering how these things work. All right, so questions so far? Okay. We're looking for the limit as x approaches infinity, and I could use negative infinity for any of these answers or any of these problems as well. X minus 1 over x squared. Now you're going to be asked these questions two different ways. So I'm going to show both ways that we're going to think about this. Algebraically. So when the problem says find the limit algebraically, it means to do what we're going to talk about next. For all of these limits at infinity, what we're going to do is divide everything by the highest power of x. Because what we're trying to do is change this, rewrite this, turn it into a problem that we've already solved into something where we can use this rule. All right, so we're going to rewrite this algebraically. So this is the limit as x approaches infinity. We're going to divide everything by the highest power of x. Highest power of x here is x squared. So in the numerator, when I divide x by x squared, what do I get? 1 over x. Divide 1 by x squared minus 1 over x squared. Over, I'm going to divide x squared by x squared, I get 1. Equals, well, what's the limit as x approaches infinity of 1 over x? Zero. What's the limit as x approaches infinity of 1 over x squared? 0. Over, limit as x approaches infinity of 1 is just 1. Equals 0 over 1, which is 0. 0 over 0 is indeterminate. 0 over 1 is just 0. So this limit is 0. Our asymptote rules, the rules that we use for horizontal asymptotes, the degree of the denominator is the largest, or larger. So we had a horizontal asymptote at y equals 0. So when we were working with horizontal asymptotes, we said when the degree of the denominator is the larger, we had a horizontal asymptote at y equals 0. These two are the same. Now our shortcut. We call this kind of function bottom heavy, because the degree of the denominator is larger. Anytime we have a rational function that's bottom heavy, the limit equals 0. For a bottom heavy function, the limit equals 0. So algebraically, we would do this and use the limit of 1 over x and 1 over x squared. But our shortcut is to say this is bottom heavy, the limit's going to be 0. And this is why this rule for our horizontal asymptote works. Because these limits are 0, we get 0. All right, questions there? Okay, let's look at another example. We're just going to do variations on this function. The limit as x approaches infinity of x squared minus 1 over x squared. Algebraically, and I'm going to do 2x squared. Just a little change. Algebraically, we're going to divide everything by the highest power of x. That's our technique. So we get the limit as x approaches infinity. When we divide, our highest power of x is x squared. So we get, when we divide this by x squared, we get 1. We get minus, when we divide this by x squared, 1 over x squared. And when we divide this by x squared, we get 2. That equals, the limit as x approaches infinity of 1 is just 1. Limit as x approaches infinity of 1 over x squared, 0. And this limit as x approaches infinity of 2 is 2. So we get 1/2. The degrees of the numerator and denominator are the same. Our horizontal asymptote rules told us that we had a horizontal asymptote at y equals ratio of the leading coefficients. I'm just going to say dot. Well, the ratio of the leading coefficients here, 1 over 2, 1/2. So that is our limit. Our limit is the horizontal asymptote. I'm not going to say equal because our limit's a number of horizontal asymptotes aligned. So our limit goes to the horizontal asymptote. We don't have a special name for this situation, so we invented one last period. We decided we'd call this equal heaviness. And I said it's kind of like equal heaviness, maybe like I said Metallica and Megadeth, and we decided no, Metallica is heavier, so that went away. So I wasn't sure what to. Maybe what would be a good comparison? Five Finger Death Punch and Volbeat? Yeah, is that a good? They're about equally heavy. I think Five Finger Death Punch might be a little heavier than Volbeat. Bucket? Oh, that would say equal heaviness. Yes. Buckethead and Primus equal heaviness, definitely. So when we have equal heaviness, the degree of the numerator and denominator are the same. Our limit is the ratio of the leading coefficient. Leading coefficients. Just like our horizontal asymptote rules. All right, questions there? nice and easy. Easy ways to find our limit. The algebraic part, not difficult. We just divide everything by the highest power of x here. All right, let's do one more. We have 3 different cases that we need to look at. The limit as x approaches infinity of x cubed minus 1 over x squared. Algebraically, divide everything by the highest power of x. So this is going to be the limit as x approaches infinity. We're going to divide everything by x cubed. So we get 1 minus 1 over x cubed over, and when we divide this by x cubed, we get 1 over x. So this is going to be, we don't need to write the limit again. Limit as x approaches infinity of 1 is just 1 minus the limit as x approaches infinity of 1 over x cubed, 0. And limit as x approaches infinity of 1 over x, 0, equals 1 over 0. 1 over 0 is undefined. This function is unbounded. And we said for our horizontal asymptote rules, the degree of the numerator is larger. And in that case, we had no horizontal asymptote. So our function either gets bigger and bigger, keeps getting smaller and smaller. So our function gets really, really large or really, really small. It's undefined. The limit does not exist. We call these kinds of functions our shortcut. These functions are top-heavy. And when rational functions are top-heavy, the limit does not exist. So that's our shortcut. Top-heavy, limit doesn't exist. So that's really why our asymptote rules that we used, horizontal asymptote rules that we used, work. It's because of that limit of 1 over x is 0. So we have top heavy, limit doesn't exist, equal heaviness, limit is the ratio of the leading coefficients, bottom heavy, the limit is 0. Those are our 3 cases. Questions? All right. I just want you guys to think about this one. We'll talk about this one for a second. The limit as x approaches infinity, because this one is a little trickier. Cosine x over x squared. So we don't really have a rational function here. So the power of the numerator, the highest power on x in the numerator, doesn't really make sense to talk about this. What would we guess this limit's going to be? Any ideas? What do you think, fellow? 0. What's the largest value that cosine x ever is? 1, right? So isn't this going to be less than? I guess it could be equal to the limit as x approaches infinity of 1 over x squared, because cosine of x never gets bigger than 1. What's the limit as x approaches infinity of 1 over x squared? 0. So this says this limit is less than or equal to 0. So our limit is 0. So with functions like this, and you'll learn other tricks like other ways of dealing with more complicated functions in calculus. So sometimes you have to be a little more tricky with our thinking. So we can't always say top heavy, bottom heavy, or equal heavy. But we always often we try to go back to those rules that we already know. So just a different way of thinking about this kind of thing. All right, homework. Let me make sure I do this right. There's one. All right, there we go.